Thank you, Alexei, for introducing me. And so I hope you had a joyful lunch in our canteen. How do you think about Chinese food in China? That's great, great, great. Glad to know that you like it. Um, so I think this afternoon we will have an ice-breaking event, and I hope the students you can really get familiar with each other. And okay, now I'm going to use my time to introduce some of my work and some of my thoughts on the AI. Actually, Professor Brunev already introduced a lot this morning, and I agree with him that the data-hungry and only data-driven AI is not AGI, and I am really interested in the engineering AI idea, the EAI idea. From my perspective and my research is that this is a recombination of machine learning based AI and the knowledge based AI, which is, you know, the good old fashioned symbolic based AI. So engineering based basically means that you need to encode and program and also make plans that can, you know, guide the agents or direct and as a workflow as an orchestra to organize the agents. Uh, so the key is how to make this representation possible. As I said in my opening speech, I worked in neurosymbolic AI, and I have been working on this for a long time. So my talk, the title today would be Interfacing Learning and Reasoning, basically joining the two sides of AI research, the symbolic side and the sub-symbolic side. First, I want to give you a first impression of this talk. I think most of you have a lot background in statistical AI or neural networks, but not all of you are familiar with symbolic AI because it's considered to be a very old topic and not many people are really interested with them. It has been there has been a converging trend that the AI community has now recognized that neurosymbolic is a very important topic. So if you are interested in this field or in general AI, you must know the ICHCAI conference, so the International Joint Conference of AI, which is the biggest conference in AI. It includes not only the statistical learning people, the neural network people, the vision people, but also many knowledge representation people and logic people. So there are I remember, 5 keynotes every ICHCAI. So last year, there are like 4 talks are related to combining learning and reasoning. So the core, I think, the core idea is that the statistic-based predictions alone is not enough for systems that must act, explain, and generalize. So Luc Dorat, who is from Belgium, the KU Leuven, so he introduces the idea of combining learning and reasoning. So last year, not only in the ICHCAI 25 keynotes, he talks about neurosymbolic AI, which is a combination of logic, probability, and neural networks. He also wrote another paper. It's called a Learning and Reasoning Manifesto. It says AI equals to learner plus reasoners. This is just like what Professor Brunev has introduced. The learners are the current mainstream AI, and the reasoners would be the planners and the orchestra, or maybe harness or workflow or anything you want to call it. They are the other side of the AI. And also for the causality side, the causality people, including Bernard Schophoff and Yoshua Bengio, they're promoting the idea of combining machine learning with causality learning. So if you know causality models, I think most of you knows the Bayesian network, Markov network, all the probabilistic graphical models. So graphic model is a representation of causal model, and what they are saying is that standard machine learning may capture spurious correlations, but not causations. So people are talking about world models and all this kind of stuff. You want to know what makes other things happen. They try to model or pushing neural AI towards an explicit causal compositional and inspectable theories. Again, symbolic representation. And also, there's another invited talk in HKI 25. It's for a young career talk, I don't remember. It's from Professor Cynthia Rudin. So she's talking about interpretable machine learning. What means by interpretability? So everyone knows that ChatGPT can actually explain a lot of things, but we don't consider the large language model as interpretable models. One big problem is that we cannot debug it. So you know the chain of thought, right? But you can't tweak the chain of thought. It's not like a program that we can identify the input and output and do formal verification and checking and then, well, do troubleshooting. So inspector models is something very, very important for AI research if we are aiming for like larger targets like scientific discovery and other kind of like human, all kinds of human-computer interactions. So there is a shared direction among the field. Is that we should learn structured models that supports inference, intervention, and diagnosis. Well, behind this, this is what I want to claim. So LLMs are powerful generators for plausible hypotheses. Reliable agents also need representations that can be executed, checked, grounded, and revised, i.e. a symbolic and formal representation is needed. So in this talk, I will cover like 3 problems. The first is that how can symbols emerge from raw experience? So you know that if you know the symbolic AI, you know that all the symbolic AI are presuming that a human-designed knowledge base. So everything is formalized by human. But actually, the failure of the good old symbolic AI shows that the knowledge itself cannot be provided only from human. There must something be learned. So if we want to bring that back, how can these symbols emerge from the raw experience, like pictures, natural languages, sounds, all the sub-symbolic representations? And then, if we have those symbols, or the system that can learn those symbols, if I have a plan, then I have step 1, step 2, step 3. How can I ground those steps into low-level perception and actions? So this is something that related to, I think, gaming, okay? So everyone play video games, at least in your age. So you have many, many plans when you're trying to play a video game, but only thing you have, the input and output, well, the input are the image and the sounds. And the output is only, you know, the joystick interactions, right? You only have a joystick and like up, down, left, right, but you have to do all kinds of high-level thinkings, like I want to open that chest, I want to avoid the enemy, and I will use the magic, etc. But what you only have is a sub-symbolic input, raw input, and also a very, very low-level output. You only have like those joystick actions and some buttons. So how can you kind of bridge your high-level intention and the low-level perception and actions? So this is the grounding problem. The third is that if we can learn a formal representation, how can we debug it? So this is another side of this problem. So if we are assuming that a formal representation is necessary, then it could be wrong, just like any program you wrote. So you need to debug. You need to identify where the error comes from and to try to revise it or even redo the whole project. So these are the 3 questions that we're going to discuss. Okay. So I will, next I will go into the, first introduce some basic layer, give you some basic background about symbolism. So why should we still talk about symbolism? Everyone knows that deep neural networks works well, pretty well. At least for large language models, all we know that it is a probabilistic model, very complicated probabilistic model that predicts the conditional probability of the next token. It has no magic. The magic lies in the big data and also the computation infrastructures. So, and also we have witnessed some of greatest successes. So from 2024, Google is already trying to use large language models to do formal mathematics. So in IMO 2024, what they are doing is using language models to write Lean programs, right? So Lean is a formal language that can do formal checking and formal proof. And then in IMO 2025, the last year, they discarded the Lean verifier and using only natural language agents to do mathematic proving. And this year, you know that the OpenAI has already achieved a great success in one of the Erdős hypothesis proving. Well, it's a disproving, but actually it's only based on natural language. And just, I think 2 or 3 days ago, OpenAI released the GPT 5.6. And on Twitter, some researchers said that they use the GPT 5.6 Soul Ultra, which can guide a bunch of natural language agents. They proved another we call CDC theorem or hypothesis, but it's not checked. But in that, in the most recent version, what GPT do is trying to use Lean to formalize these proof and then trying to do the verification automatically. So anyway, mathematics seems to be kind of solved by large language model, and mathematics is something that we think formality or formalization is most important. So why do we still care about formal representation? So in this year, in June the 2nd, many mathematicians has signed or at least endorsed the Leiden Declaration on AI and Mathematics. If you know that, they have major claims about LLM-oriented AI or mathematics research. So the first thing is the unreliable proofs, because LLMs only produce plausible outputs. It may be incorrect and hard to verify. And also, the model synthesizes many human work, but it doesn't really properly giving the credit to the human mathematicians. So it have weak attribution to the person who really contribute to the mathematic problem. And also, there are some other problems like distorted incentives. So for students who are doing maths right now could be kind of discouraged because many efforts has been, can be replaced by large language models. And the bypassed evaluation is something that publicity can precede rigorous peer review, which means that we have so many proofs generated by AI, but we cannot really evaluate them. And finally, they are worried about the loss of autonomy, which is the core and the most precious part in mathematics community. So these are the reasons why we should still head back to a formal reasoning path, or at least a formal, a human understandable AI development. And also last year, the AAAI 25, the president, they had a president panel, and as you can see, actually for AI reasoning and AI like trustworthy AI or AI safety and AI for social good, there are so many things that people are really worrying about. The data-driven or the large language model that cannot explain itself will bring many problems. And one of the keyword they had in the main takeaways here. So people think that at least all the AI researchers present in AAAI conference thinks that these large language models or machine learning based AI only provides plausible hypothesis. Like I said, it appears to be true, but you cannot verify it. At least AI itself cannot verify it. So why we want to bring logic back is that logic has its soundness guarantee. So here is a very simple example. So if you read that, this is a cognitive science term. It's called subtizing, which means if there are a few items in front of your eyes, if the number of items is less than 5 or 6, then you can get the number of the items just at one glance. But if it is more than 5, or even much more than 5, you need to call algorithmic reasoning procedure. So the so-called system 1 and system 2. So system 1 can actually guess the number of items and get it very, very close, the answer correct, if the number of items is under 5. But if it's more than 5, then you may need to do the system 2 reasoning. You need to call an algorithm in your brain and trying to count the things one by one. So this is a very interesting experiment. So I showed that last year to the GPT-5 5.1. So as you can see, the GPT-5 5.1 agent can do this. It tries to use some programming to count the fruits. This is correct, right? As I said, the subtizing problem is very difficult. If you count too many things, then you need to do that program as a program, use algorithms or use counting algorithms. So it starts to writing the code and tries to use OpenCV and trying to write a Python program to count this. So I'm not going to play it fully. It lasts about 1 minute. It did a lot of things. So if you counted this image just now, you will see that there are 6 apples and 11 oranges. So this is what the agent of GPT 5.1 did. The first trial, it uses color mask. So what is a color mask? It filters out all the green components and also filter out some the orange component. So there are some connected green regions and connected orange regions. It got wrong answer. And then it thinks that, okay, those fruits are balls, right? So you just need to fit some half circles and trying to count the circles. So it got the wrong answer again. Then it tried to tune the parameters and also did some sampling of the points and also using the watershed algorithm to do some basic image segmentation and then cluster it back again. Finally, it tries to manually fall back to count the model, to count the fruits. So the ground truth, let me see, the ground truth should be 16, but it actually gets, should be 17, I think. Yeah, this last one is wrong. So anyway, it gets the wrong answer again and again, and just fail this task. I also tried to ask the GPT 5.5. So what GPT 5.5 does is that it has an image processing component. So you can ask it to try to label all the fruits here. So you can see there are some hallucination here. Apparently there's nothing here, but it labels here as orange. And also GPT 5.5 got much better results. So you can see it's just like the Meta's SAM. It can do segmentation. And this segmentation appears to be correct. So you can see this is an apple and this is an orange. But you can see some very weird tagging. So this orange is labeled as an apple. And also there are some oranges are missed. So again, it is wrong. So finally, I tried with some with codecs. So I think codecs should be good enough because it has really powerful. You can use it can use CLI to do really hardcore coding, but again, it did a lot of things, and it provides a wrong answer. So the oranges should be 11, but actually the results are wrong. So I have did this for a long time. So these examples I have fed to the large language models. Firstly, like in many years ago, I think 2 or 3 years ago, but this problem is still unsolved. And you can see this is the result generated by codecs. It's still wrong. So what's the problem? What's the problem? So in GPT-5's formalization, the concepts apple equals to many, many things, like green connected regions, green circles, green segments, or green clusters. Orange is some of these terms, but in another color. It could be anything definable with the existing Python function, just not apples and oranges. So this is the key problem. So if we assume that we are really doing accounting, we should define the symbol of fruits and then just use a very simple program. So I personally use a lot of Prolog, which is a logic programming language, but you can regard them as a very, very simple Python sketch or something. It's very simple. So this is, so from a neurosymbolic guy's view, it would be very easy to do this. You just correctly define the semantics of the fruits and then ground it into images and then just call a higher order program to count it, then everything is solved. So why we want formal logic? So this is a very, very old topic, I think from Aristotle and to Leibniz and then to Hilbert and then Turing and Gödel and a lot of people are working on this. So plausible reasoning is something that language brings to us. So one of the job of Leibniz, I don't know whether you know that, Leibniz is a solicitor. He's a lawyer. So what he doing all day is trying to arguing with other lawyers. So that's why he emerged the idea that if we can make or formalize the arguments into mathematical calculations, then we can just, there would be no need of any court or any kind of tedious argumentation. We just need to sit down and bring us a pen and a paper and say, let's calculate. Then the case is solved. So this is why mathematicians want formal logic, is transforming the plausible language into a checkable inference. So comparing to natural language, if we want to say if there are 16 fruits, 6 apples and 10 oranges, sounds quite precise. But formal logic will make this commitment more explicit. So you need to define what counts one object. And if it is under occlusion, whether it is still an object. And also, for all these objects, you need to assign them like 2 names. One is apple and one is orange. And then, after you're gathering all these observations, then you can just do the numerical conclusion by just counting it, because the idea of number is something that we preserve in our minds. So comparing to natural language, you can have something like in the right side of the slide. You can define what is a fruit. So a fruit, at least in this context, is an apple or an orange. And then you just count. You can grab the set of all the fruits, which is in the image, and also the object is a fruit. Then you just count them. So this is formalization. It gives you a big flexibility and also explicit commitments, and you can check it, you can revise it, you can debug it, and you can change it in anything you like. Okay, so that's what we really want to do. So for first order logic that we are using right now, you have to define something we call a syntax. So it's a language. The language have some constants, and then have some functions, and have some predicates. And after that, all you got is from off the shelf. So you got the implication relation, and also the negation, and conjunction and disjunction. So those are shipped already with logic, but with different system or different language, you can use logic in different scenarios. So a formal signature is something that really important. For each different problem, we need to invent different language or different formal language. After we define the language, we need to define the semantics. So what is truth in your language? So here, at least from a neurosymbolic view, you have something subsymbolic, right? And then something symbolic. So for example, the X here are some images. It don't have any symbol in it. And then you use some perceptual neural networks or something like segmentation things or object detection things. You can interpret them into symbols. Actually, this is what we have done for a long time in machine learning. Do image classification, right? Do all these, I don't know, the ranking predictions and also the recommendations. It's trying to create some symbols from the data that do not have symbols. So this is what we have done for a long time. And then if you have some background knowledge, which is the B here, then you got these symbols which is interpreted from the subsymbolic data. You can do some inference, some kind of logic inference. So what we have would be something like this. So the X would be the pixels or the sensory data like the image before. And then we have some neural network to do perception, which translates the subsymbolic stuff into symbolic stuff. And then the symbolic facts would be the objects or the basic things in our set. And this set is an open set because it doesn't have any name in it. Then you got some background knowledge. The background knowledge defines your language. And this language will assign names to the objects you discovered. For example, it also contains the count function or any other kind of functions that you define in your background knowledge, and also defines the notions of fruits. And finally, you need to use it to do a logical inference. So what you do is that based on this image and also the neural networks that extract those objects and the background knowledge that does the counting and assigning the labels, you can derive a conclusion that fruits in image has 11 or 12 or something. So the notation here, we call it models, or in LaTeX is a V dash. So it's basically a vertical line with an equal sign. So it means entailment. So entailment is something defined in logic. It's a relation between its preposition and conclusion. So gamma implies, or gamma entails phi, means that phi is true whenever gamma is true. So if you get a correct background knowledge, and also you can perceive the correct object from the images, then you are guaranteed to get a correct result. So we have been working on this for a long time. So my PhD started in 2013, and I was working on combining probabilistic models with logic. And in 2019, my supervisor and I proposed a new framework. It's called the abductive learning framework. So it combines two things. So the left side is machine learning, traditional machine learning. You have some labels and some data, and then train a classifier. So what it might become a problem is that the classifier is undertrained. So it generates some labels, but these labels can be wrong. So you fed these labels into a knowledge base. So this side is pure logical. And then the logic side can do some reasoning. And this reasoning, we call it abduction, but I'm not going to too much details into like deduction, induction, and abduction. But anyway, this abductive reasoning can do some corrections. For example, I want to make sure those output of the machine learning models to be correct. I don't know whether it is correct, but it at least should be consistent with my background knowledge or consistent with the rules that we defined. Then it will do some maximization or some optimization to minimize the inconsistency between the knowledge base and the interpreted symbols. For example, changing the sign of C, negative C, into a positive C. And then this is the most consistent output, or that should be produced by the machine learning model. And then feed that back to the classifier, it will do an update, and the cycle goes round and round. A formal representation, or another kind of example, which has been borrowed by many colleagues in neurosymbolic AI, is this. So these are the images of MNIST numbers. So everyone should be very familiar with that. So you have the program is called sum, but you're summing 3 images. You got the answer 15. You don't know which number is this. Which number are these images? So actually what you want to learn is that I know the background knowledge of summing, and I know the input is some images and output is a number that should be reasoned or something like that. Then you need to figure out what are the numbers. So this is the abductive learning problem. So what we want to do is we have 3 parts. The first part is statistic learning. For example, neural networks, what does it do? It's trying to interpret just mapping raw data into logic facts. But please note that these neural networks are something that we usually assume is not trained on this data. So basically, it doesn't see anything from this. And then what you got is a logic reasoning part, the logic programming or any other kind of Python programs as well. So you can have some background knowledge and some hypothesis together with those logic facts interpreted from raw data. You can do an entailment. So this whole model can work in different directions. So if you have a pre-trained function here, a pre-trained like MNIST recognizer, then you can directly just apply it to translate these numbers into some, the images into some numbers, and then put it into your background knowledge and do the inference. So this is called deduction. So you have some general knowledge and have some observation, and then you get the conclusion. Well, this is what Sherlock Holmes suggested, the science of deduction. And then you have the abduction. So this is the other side. If the F is not trained, because we are machine learning people, right? We want to train machine learning models. So the machine learning model, like how to interpret these images into numbers, are unknown. So what you want to do is basically using these output, because this is supervised information, and then use background knowledge to abduce the results of Z. So for example, if you have known that this 15 is a summation of 3 numbers, of course it couldn't be 0, 0, 0, right? So you only have like a few options from it. Then these will give you a best candidates to train the neural networks. And then the neural networks, after it have kind of trained enough, it will kind of get the idea that this is not 0, this might be 1 or 7, this might be 3 or 5, something like that. Then you get a narrower and narrower guessing. And this kind of learning can happen by doing a cycle like I introduced before. So this is the abduction. The third version is that the background knowledge is not enough. So there is a hypothesis. Imagine that this is not, this sum function is not defined. So you don't know how to do summation. You only know that there is a function converting these 3 images into a number. Then you need to learn, or at least induce, the function here, or synthesize the program here. This is very similar to what we are doing now using language models. You only know the input and output, but you want to learn the workflow or learn a kind of skill to do this. So this is a knowledge induction part. So finally, this is the trickiest part. So the optimization problem. As you see, this is differentiable, and these are discretized and cannot be differentiated. So you have to combine these two things together and trying to optimize them in one end-to-end fashion. So this is basically what we have solved in previous years. Just a few more notes. So there are some existing probabilistic model for logic semantics. For example, Sato has proposed the distribution semantics, which is basically define possible world from possible probabilistic facts. So for example, the image here, if I want to train a neural networks that do the interpretation or the perception, you have all these kind of logic facts. For example, this image is 0, it has a probability. This image is 1, it also has a probability, etc. So for each image, you have like 10 options, and each option has a probability. And then it combines into a possible world. If you have the independence assumption, you just time them up, right? You just time the probability of 0, 0, 0, and then you got the first probability. So this is the semantics that we want to ground our symbols into this unknown world, or at least a world with uncertainty. And these can be formulated into a very big optimization problem. It combines these are the probabilistic part, and you have search part here. Well, it's very difficult. So you have to do some few more transformations. For example, the H here, as I said, is something very important. It's a missing hypothesis. It could be a program to be synthesized. So you cannot really optimize it. So it becomes very hard to optimize. And this was and the biggest problem is that it is non-convex and also very, very, it's not just non-convex, it's discretized. So you don't have anything like gradient or anything. You have to combine the search techniques with gradient descent together. So I'm not going to talk about these previous work that we have done. Anyway, we got some recognition from the community. For example, we have won the AAAI Best Paper last year because of our recent work on how to combine this neural and symbolic optimization. And as I said, Luc Derat has written a new paper called A Learning and Reasoning Manifesto. His claim is that AI equals to learners and reasoners. If you can see, he says that the abduction-based system is an ultimate type of neurosymbolic AI. So I think most of the people agrees that integrating learning and reasoning by interfacing with them some of the logic groundings is the correct way. However, this is very difficult, so he also left a note here. This is the open problem and very challenging to optimize or very challenging to solve. So as far as we know for now, we still have some formalization. For example, I have defined what is a fruit. So fruit is an apple or an orange. And the number of fruits could be just put another program in your background knowledge. It's called find all. So this is a keyword in Prolog. So basically, it just extract all these fruits out and then combine it into a list. And then you just sort the list or just measure the length of the list. However, those functions, as I said, you need to create them in the beforehand. So who create image 2, or who create the predicate apple or orange? And how are these predicates and object grounded into pixels? Machine learning, but when it is really happened, is actually when we defined the background knowledge. So we need to provide a language for this neurosymbolic system to work. And also how to check that, whether this is correct or wrong. So you need a really, really clear feedback from the raw data to give you symbolic feedback. So this is something I think former neuro-symbolic people haven't thought of. So logic checks the inference after formalization, but it does not automatically obtain the right formalization from experience. So if you notice the news, Richard Sutton, the Turing Award laureate last year, who basically invented the term reinforcement learning, has opened a new company. It's called Options and Knowledge, OAK. So his company name is called Oak. And he also hired John Carmack. I don't know whether you know this guy's name, who wrote Doom. Yes. So they are together, started a company to do options and knowledge reasoning or something like that. But what his idea, I think, is almost similar to mine, is that knowledge is important, like the options he proposed. And knowledge is important because options are in symbolic form. But what really important is that the bitter lesson we have learned. We put more background knowledge in AI that it fails much, much more than we expected. So all these symbolic representation or formalization should be learned rather than predefined. So the problem is back. Actually, when in the dawn of AI research, just 1957, 2 years, 1 year after the Dartmouth seminar, Alan Newell and Herbert Simon already proposed an idea called general problem solving. So what is general problem solving? So you have a general problem, and then the computer scientists formalize them into a symbolic form, and then just put the symbolic formalized problem into a formal reasoning engine or a computational engine. Then you get the results. So what we have done for so many years, we are still working on this, because the formalization are always proposed by human. So for example, the good old-fashioned AI, the symbolic one, logic programs written by human, probabilistic graphical models, the structures, very difficult to be learned. I think Bernard already touched that, about learning the causation graph, right? The causation graph, you have like sharp P complexity. It's still very difficult to be learned. So in most of the engineering side, we define them at the beginning. And then the statistical AI, the SVMs, right? You need to design and write the loss function and the regularizers. And then now we have agents, the agentic harnesses or the workflows. Even now they call it loops. So all the formalizations are presented by human. And actually, Stuart Russell already criticized the AI community for a long time. This is one paper, his paper in 2015. He had a major argumentation with symbolic AI people, although Stuart Russell himself is a symbolic AI person. So he said that the uncertainty is about the openness. You don't know the existence of objects before you define it. So this is something I think artificial intelligence hasn't touched until now. Finally, I think it's the time that we need to extend NESI. So for the classical assumptions, you have a fixed vocabulary for all these kind of like image classifications. You have a fixed set of labels, right? For the large language model, you have a fixed set of tokens. So every vocabulary is fixed, but imagine that how people invented square root. So every ancient mathematician knows that the existence of square root, because the diagonal of a square, you must have a number to represent its length. But in their vocabulary, there is no such term to define this. So we extend our vocabulary. Logically, we say this is a Scholen function. But anyway, you just invent a new symbol out of blue to extend your vocabulary. So this is the first problem I want to discuss. How can symbols emerge? So this is a problem of abstraction. The second one is the fixed grounding. So you only have like fixed number of actions and fixed high-level intentions. But how do these symbolic predicates acquire perceptual and action meaning? Which means if I define something, I'm playing Zelda, I want to use sword to kill that goblin. So this is a very symbolic intention. How to ground that into a sequence of actions, low-level actions, and execute it and make sure it accomplished correctly. So this is the grounding problem. The third is the debugging problem. So in previous neurosymbolic AI, even in most of the symbolic AI, old school symbolic AI, in knowledge system, expert system, anything like that, you assume that there is a correct theory. So all these rules are correct. They are golden standard. But humans make wrong knowledge bases all the time. So how to formally represent a repairing procedure of your theory? So this is the third problem. How can we debug them? So the main idea of my research, or the whole story, we can summarize that in one sentence, and I think it will still continue for a long time. The symbolic interface itself becomes an object of learning. Okay. So now I'm going to start to introduce the first part of my talk, not my work. So it will be a very, very brief introduction, but I hope you get the idea. The first one is the symbol abstraction. Suppose that you are playing in a game in a grid world. So you have something, this is also proposed by OpenAI, it's a mini grid environment. You have a grid like this. The task is to make this agent to reach to the goal. And you have only low-level inputs. The raw image, I'm not saying that these segmented or already grid-like inputs. It's an image with like 320 by 320 pixels. So every input are the pixels. There are no symbols existing in this environment. What you only have is low-level actions like forward and turn left, turn right, like pick up, push down, and also toggle something. And then you only have one reward. The reward is here. All the other actions, you don't get any reward. So the original problem, you can define that in a MDP, a Markov decision process. So you have some raw original image like this, and then you have low-level actions. You push forward, then the image changes. Then you push turn right, the image changes again. And then you have some state transition of low-level actions. So these are implicit. You have to learn that. Suppose that we have symbols, right? If we have symbols, then it can be very easily defined. For example, I can define this whole process as a state machine. So if you have something called K, then I said the semantics of the symbol K is hasKey, and U is door unlocked, and G is I'm at the goal. Then you can segment this task into 4 stages. This is the first stage at the beginning. You don't have the key is locked, and you are not at the goal. Then you have to fetch the key and then unlock the door and then get the goal. So this is the very, very simple representation if you have symbol. But you don't have the symbol, then how can you convert such a continuous sequence of this into 4 stages? So this brings back us. What is the meaning of a symbol? So let's think it in states. So for example, this is when I traveled to Finland. I walked into a forest and I want to rest. So, but there is no seats, right? But actually I can sit anywhere. So it makes me think the concept itself is not just a visual representation. For example, the idea of chair, if you put that into any large language model or any visual language model or any image classifiers, you can get a very good prediction because it has been trained on so many chairs. But chair is not just a visual sign. Chair is a state changing function. So this is chair. Chair can make me transit from stand into sit. Of course, I have to do it voluntarily or at least comfortably. If you hit me on my head and then I sit, I don't consider that hit. So this is the basic idea of our first work, is that we can learn abstractions by learning abstract states. So we define something we called abstract state machine. I'm not going to too much details about it. For example, if the state machine is a raw state space, if there are two states has been learned, then the agent was kind of positioned in the unknown state. Then it can do something we call exploration, right? Do some random exploration. When it did some random exploration and reached to some states that it recognized that, oh, I have been here before, then it collects the trace and use the abductive learning framework that we made before. It can explain this trace and segment it into 2 or 3 more stages. What we finally get is something like this. It tries to invent these new stages, and as you can see, it invents, in our experiments, it invents like 4 very important states. And those states, for example, the first state actually implies a key has been acquired. So although we haven't defined anything called key, but we have learned a program called like this. It's a stage program, so each state we learn as a state transition function as a reinforcement learner. But these states actually implicitly encodes the symbolic information behind this scene. So what we tried before is something that reinforcement learning can really be bad of. If you did some reinforcement learning before, you know that if reinforcement learning is trained on one map, then it definitely not work on the other map. So what we've done is we use 5 maps for training and then test it on 50 maps. All the maps are arranged like differently, randomly. As you can see, the results are very good actually. So when the state changes, the learner will have something like a performance drop, but then it gains, because it tries to learn, when it has meets some new states, then it tries to invent a new state and then trying to learn in that new state space. So it goes back and goes back. And actually the performance is quite good, even without any pre-training or any post-training. It can also generalize to unseen maps. So the problem becomes like this. So this is the first summary of the abstraction problem. So here is an under-trained agent. Imagine you are the agent that playing that grid game. Then what the agent sees is something like this, right? Because it's not trained in this sub-symbolic environment. You got only a bunch of noise. Then you see an action. It becomes another bunch of noise. And then you see another action. You see another bunch of noise. Then you collect a lot of noise sequences. Then you pop up, you got the reward. And you want to learn what happened between this noisy information, right? So what you really want to do is, what we have done is we modeled something. We try to make this model to learn some regular grammar, because regular grammar is very good for representing states. And then this grammar has an infinite alphabet, so it can keep inventing new symbols and then trying to induce some rules to represent represent the relations between these symbolic states, and then combine these abduction and induction together to do the learning. So we have some preliminary results on this work, but I think this is a very, very important problem So I really want to encourage everyone to kind of think about it. And then there is the symbol grounding problem. Okay, this time again, I'm also playing a game. So the target is maybe, this is a 2D version of Minecraft. And the target is to collect some wood and craft pickaxe, and then mine some stones, something like this. Then how can you make this intention to be executable in this environment? So the goal is expressed in language, and the observations arrives as pixels. And execution really requires low-level actions all the time. You don't have really like predefined actions that do a bunch of actions to do one thing. So language models can do many things. It can write some formal programs, like this kind of state transitions. For example, you need to get stone. First, you get some wood pickaxe, and then mine stone. If you want to get the pickaxe, you need to collect some wood, and then craft the wood pickaxe. So these are the state transitions. So the X and Y and Z are the states which represented in the state space. So defining these predicates is very important. LLMs can do this. But what really they can't do is to ground these predicates in this reinforcement learning environment. So long story short, we have done something, we call it compile, ground, and execute. So there is a large language model tries to generate formal programs, and these general logic programs, which are the formal program or the so-called maybe workflows, these workflows are grounded to reinforcement learning policies. And these policies will be fed back into the environment and collect some trace, and then to do this implementation circle again and again. So for unimplemented predicates, it was treated as what we call abducible reinforcement learning model, and then the language model will treat these abducible models and as a function or reinforcement learning function, like in Python, and then try to write the reward function, and then deploy itself into this environment and trying to learn this predicate. So once a predicate has converged, it will be registered as a reusable predicate in the library, so that in the future, if I want to collect more stones, I can recall this previously defined predicate. So we have some basic assumptions. So the agent, at least, I think, is fair for human as well. The agent can monitor their cells states. For example, whether I have a microphone in my hand, whether I am happy now, whether I have enough health in this game. So these are something that the agent know. But for all these other stuff, the visual side, we assume this representation is pure subsymbolic. So we did some experiments comparing it to large language models only, and also some reinforcement learning. So you can see for this Qianwen, it can solve some problems, but for some harder problems, it cannot accomplish anything. And then if you use like end-to-end reinforcement learning, you can get some good results in simple tasks, but for a harder task, it becomes really, really bad. And then if you combine them, use large language model to generate the formal program, to formalize the problem, and then ground them into reinforcement learners, then you can see a lot of boost in these results. And moreover, it not just only ground the predicates, it also invents some new predicates that it requires. For example, if you want to make a very complicated item, the iron pickaxe, you need to place a table or place something. Then, although the plan does not have this place table function, the large language model can invent it and then ground it. So now our next question is that what if this formalization is erroneous, is wrong, or at least is buggy. So this leads to our third direction of exploration, which is debugging. So here is another very popular benchmark. It's called ArcAGI2. It's for abstraction and also planning as well. So you see an input and then you predict the output. For example, here is something that you connect these two and then swap the color of yellow into here. The yellow has a red inside, so you swap this color, and also these blue are referred to the green here, so you swap the color here. So what you basically these benchmark want to do is to construct a program, a formalized program that can convert these pixel inputs into the pixel outputs, but without telling you any background knowledge about what kind of transformation you can use and what kind of object are defined. So without large language model, this problem is basically unsolvable. So what we want to do is that LLMs can actually solve part of these programs, but usually they have very buggy program at the beginning. How to revise the buggy program and make it better and better, just like human debugging a program. So again, we think about maybe we can use Prolog because Prolog is a very, very good language for abstraction. I know it's very old and almost dead, but actually it's a very, very neat and high-level language that I think it simulates human reasoning pretty well. So that's why I keep using it. So comparing to Prolog or pure large language model, we can really generate candidate abstractions and trying to debug it. So this is another good side of Prolog. For example, if we learned some transitive reachability from a chain with only 3 nodes, you can define something like this. A reachable is an edge, or a reachable is 2 edges. So this is a correct program, at least for this test data, right? But actually, if you think this is a transitive closure, you see, well, why not we just define a transitive closure by doing recursion? So if you apply this program on the chain with 4 nodes, you will see that there are some examples failed, some examples succeeded, and some other failed as well. So this is when Prolog becomes really, really useful because it expands all those program executions into traces. It's a tree, and these traces actually records all the input and output of each predicate calling. So it will be very easy to debug this. Once the large language model sees the AD fails, it will suddenly understand that, okay, this is what I really want to define is a transitive closure. So using reachable to replace this edge would be much, much better because it will covers more and more, almost, well, infinite numbers of examples. So by providing this kind of trace to large language models makes it more easier to debug its own programs. So here is what we have implemented. We use second order logic. So this is a meta interpreter in Prolog, which means use Prolog to explain or interpret Prolog. So it's a higher order programming technique. And then it can be combined into one system. So this interpreter will change. So at first, the neural networks or the large language model generates some program. And these programs are written in Prolog. Then we apply these programs into the test data. If it fails, then it will expand the proof tree of Prolog proofs. So all the program execution become a logical proof. Then the proof can be expanded in a tree. Then you just need to identify which part causes this error, and then put it back into neural networks, put it back into large language models, then it tries to debug the code. So we did some experiments. So the first experiment is that, you know that for large language models, a lot of people are doing execution feedback repair. I think everyone do vibe coding are working on are using this, right? When you get some error, you just copy all the error message and paste back to the agent and say, okay, this is wrong. You need to debug it again. So this is the first version, the vibe coding version, execution feedback repair. And the other one is the proof trace, which we have proposed. You can see in Gemini 3, we already get a lot of boosts. So iterative execution, this kind of vibe coding repairing is working. It can boost like Gemini 3 from 34 to 49. It's a great improvement. But if you provide trace, then it gets better. And then Gemini is not good enough. So we tried GPT. How about GPT? Then you can see that in GPT, we can improve its performance much, much more by getting a nearly 98.300 success rates in the test case. So I think this is the highest result for now, in ArcAGI public set test. So we also sent these results to NDIA, which is basically founded by Francois Chollet. So ArcAGI challenge is proposed by him, and he's very interested in our results, and we are trying to collaborate to do some more tests on the private set. So as you can see, the GPT 5.5 can reach very good results, and even Gemini 3 can get better. But unfortunately, if the large language model is really, really weak, for example, the Claude Sonnet is the tiniest model that in Claude, you can see the initial result, which means that the initially generated program is very buggy. Then this improvement can be very wrong. It's just like if you are asking a pupil to write a program, then it will be very difficult to help him debug the code, something like that. And unfortunately, we would like to try other Claude models. Then the Americans start to invade Iran, and we cannot use Claude anymore. Okay, so we also have some results on Raven as well. You can see by using this code repairing technique, using Prolog traces, is much, much better than the naive vibe coding debugging. So finally, we have proposed an integration tool to combine the logic reasoning side, which I think logic programming is a very good tool. And also the other side is Python based. Basically what it do is Python, doing all these machine learning reasoning or something. So the problem is that the logic must to call neural code. So this is something that we think very differently from previous neurosymbolic guys. So every neurosymbolic system, if you are interested, you will see that there is a Python module is calling a logic side, calling a logic knowledge base, or calling an outside source of knowledge graph or something. But we think that this is totally different. We think reasoning or high-level reasoning should be something as an entrance of the whole task. So we think that logic should call Python instead of Python calling logic. So this is why we make this tool. So it calls Python perception and can do some reinforcement learning policies, and it can exchange tensors and exchange the structured values. And also it preserves the best thing, it preserves the resolution. So resolution is a technique in logic reasoning. You can see it as a sound and complete reasoning in horn clauses, which is the language of logic program. So this preserves the original formal reasoning. It's not chain of thought. It's not any kind of plausible reasoning or so-called reasoning. So this is hardcore reasoning. So you can do backtracking and do expectation. And for example, the real challenge for us is how to preserve this kind of logic control. So we still put the neural libraries inside of Python and then build a bridge to combine these two things together. So this interface is actually from the theoretical perspective, the interface is a part of the semantics. It's not just plumbing two languages together. We're using Prolog to define the syntax and using Python to implement the semantics. So this is it's a very simple combination, and my students basically use Claude Code to write this. So I think if you have idea and you can get access to strong language models, you can do research pretty easy. This is something that I cannot imagine when I was doing my PhD. So anyway, the logic part, Prolog defines the rules and have the formal resolution reasoning and resolution-based reasoning. It can do backtracking, and most importantly, it can goes up to higher order reasoning, so do meta-interpretation. And also the Rust will be something in between, and then Python is doing the language model or vision or anything like that. So here is an example. So one good thing is that now the Python failures can enter Prolog control. So which means when the semantics in the Python, like in the image recognition or language model calling, you get some failure, your logic side will immediately get a notification that this is failed. And also logic control still survives. So once the grounding is failed, doesn't mean the whole program is failed. You can do backtracking and do some other stuff to try another rule or anything else to just report the error to the caller. And also a CNN or something like neural networks can be directly modeled in the logical reasoning side. So you can just define Python calls inside a Prolog rule and define them and call them using pure Prolog rules. So I think I'm using almost all the time. So this is the conclusion. So I think the open world neurosymbolic AI, or the I think is open world AI in general, it should be neurosymbolic. And we need to learn the interface. The classical neurosymbolic assumes a fixed vocabulary or fixed grounding or a correct background theory or a fixed implementation. This is what I have added. So now we need to learn how to abstract and how to ground and how to diagnose or debugging and how to make a tool really combines these two things together. So neurosymbolic interface should itself be a project of learning, reasoning, execution, and revision. So this interface is more important than the two sides, which has already been studied for a long time, right? Symbolic AI for 50 years, and now another nearly 50 years for sub-symbolic or neural people. So now is the time to build the bridge. The Peter lesson warns us that we should be careful about the hand engineering knowledge. So formal reasoning supplies explicit semantics, composition, proofs, and debugging. Those are very high level ideas. It doesn't really define the knowledge or define the object or the targets. The only thing that open world neurosymbolic AI should do is to learn the vocabulary or learn this language. So in one sentence, you do not need to discard formal reasoning, but you should learn the formalization. So here is the last slide. So I think in human AI, we have system 1 and system 2. People think that, okay, we have system 1 and system 2, then okay, this end the story. But actually, there are so many things. You have sub-symbolic environments, you have perception. Then the perception abstract symbols. These symbols goes to knowledge, and this knowledge helps you to decide. Decisions are high level. You need to ground that into low level actions, like how to move in your muscles, right? And then those actions will affect this environment. So the real tricky thing is inside here. So these 4 blocks: perception to abstraction and decision to actions, and also how to debug the whole thing in a final loop. So I really love Sutton's paper, The Era of Experience. And I think what he really claims is not the end of human knowledge or human data, but actually the combination of the neural and symbolic side, and how to learn those symbolic things from data instead of defining them. And thank you very much. And these are the works of my students here, and I want to thank them as well. Okay, that's all. Yes, please. You.
Yeah, so
Yes. Okay.
yeah, so because otherwise it don't work. So you Раз,
Yes.
раз.
Okay.
Yeah, yeah. So in the very beginning of your lecture, you demonstrated a formula where it was a variable age, right? You told that it's very difficult to optimize with respect to age.
Yes.
Is it possible? Why not to infer this in expectation maximization algorithms?
That's true.
So we, of course, we cannot optimize with respect to age, but for example, we can sample age, say using MCMC, Monte Carlo,
Yes.
Markov sample, Markov chain, or something like this. And then, given age, we can optimize that probability and then repeat. So wow.
That's true. Let me get back to the slides. Actually, there is a small error in my slide. It doesn't get through. What I have put here is that we were really doing expectation maximization here. Let me see. It should be here. So it's the, I think it's the here, non-convex, right here. Okay, let me refresh that. Here. I think you are mentioning this one. Yes. Oh, sorry. This one.
Yeah.
That's right. So it got, if you notice my previous slide, it only has this one, but actually it has this. It can converge to suboptimal by EM algorithm, so that's what we are doing. But H has still a very big search space because the hypothesis space is very big. So what we did is using an abduction-induction theory. So this is something from second order logic. So it can actually kind of, prune the search space a lot. So it makes this learning possible. So yes, using EM and MCMC is an idea to do it. And I think using MCMC is even better because you can do parallelism.
But you haven't tried still yet, or you already tried that?
Yes, in previous work we already did this.
Okay. Another question. Have you explored the relation between this induction, abduction logic and topological spaces?
So it's very simple actually. The idea is very straightforward actually. So if you see this is the sum of three numbers, you get a 15. Then there are a lot of assumptions you can remove, like 0, 0, 0. This is something doesn't exist. So if you have the background knowledge of summation, then this space can be shrinked a lot because you don't need to explore all of them. And also from the other side, the neural networks, when it goes back into the abductive learning circle, it kind of converges to some point. Even it is not perfect, it will understand like these two images are different. So it will assign like two different labels to them. And the visual difference or the low-level distance between those logic symbols, the groundings, they also provide another signal of pruning the search space. So both the machine learning side and the knowledge reasoning side will help to reduce the hypothesis space size. So that's why we call it abduction, induction.
Yeah, I
Technique.
understand, but what do you think? What could be the best option to connect this with topological persistent homology idea?
So I think what you have discussed in your talk, like the using manifold or this kind of concept representation in embedding space, I think this is something kind of related as well. For example, we know that the word embeddings, they actually survived in a manifold space, right? So it can represent many, I don't know, the vector relationships between concepts, and those stuff reflects there are some structures can be learned pure subsymbolically and can be represented. So I haven't tried this before, but I think the topological structure behind those groundings can also be another source to, I don't know, increase the efficiency of the system.
Okay, understand. Thank you.
Yeah.
Thank you very much for a very interesting talk. Well, I have a naive question. So what you've shown in this diagram, when you had the fast and slow system and then the intersection. So at the time I was thinking, so wait a second, this applies to logic, to hard symbols, but maybe you've thought about this already. So what if my symbols are fuzzy? So have you thought of expanding your framework to something like fuzzy or granular computing concepts?
Yes,
Thank
this is a even classical topic. So fuzzy logic is something that neurosymbolic has been explored like I think for many years, and also recently, and 10 years before, a lot of people are defining like T-norms or all these kind of fuzzy operators to use them to approximate logic reasoning. So what I think is that fuzzy logic is kind of, well, it's semantically, it's not logic. Yeah. So it's a function that defined to approximate logic, but it doesn't hold the consistency or the soundness. At least it doesn't has the soundness guarantee. So my own opinion is that I want to keep the logic side in just a classical definition. But for if you want to, I don't know, if you want to accelerate the logic inference, you can use fuzzy logic and maybe use differentiable logic, which is much faster and kind of is quite useful. But if you want to really learn hypothesis, then it becomes a problem. You need to reconstruct the hypothesis all the time, and then to do the calculation. But for fuzzy logic or probabilistic logic, you for every structure of the hypothesis, you need to fit the parameter.
Yeah,
This is big.
True, I got it. But I think let me dig a little bit deeper, because the motivation was as follows. So, for example, suppose that I want to use this framework in robotics, and I want to produce a machine which I can verify and trust, and which I can also learn from experience. Now, at the same time, in the back of my mind, another picture emerged, a cat or a dog.
Yes.
They are animals, and I bet they don't have formal logic woven into their brains. Therefore, they operate somehow, you know, in the very same way which is shown in your illustrative example, saying, look, we can count apples and oranges if there are, you know, maybe up to 5 of them all present in the picture. So we are doing it using the fast system.
Yeah.
But the fast system is fuzzy.
Yeah.
Because it doesn't know the concept. Well, it may have a concept of something like an orange, something like an apple, but not crisp concepts. And that's why I asked about this, you know.
I see.
Yeah.
So it's two. This is actually two. These are two questions. So first, I think animals do have formal reasoning power. So there are some. One of my good friends in working in neuroscience. He's in Shanghai. He had a paper and proposed an idea. It's called the language of problem solving. He taught the monkeys to play Pac-Man. And then they find that the monkey actually learns a grammar tree of the policies. For example, when the, I don't know, the ghost come, then the monkey should evade, or the monkey should eat the surrounding beans and then goes to another place. So it has different kind of symbolized strategies, and these strategies forms a tree, which are rules. And further, he did another experiment to compare the grammar tree or the tree of the language of problem solving between human and the monkeys. What he discovered is very interesting. Human have a much more complicated grammar tree, and human has new vocabulary that monkeys doesn't have. For example, human have some strategy called save. So if you played Pac-Man, there are energizer, the big beans. If you eat the energizer, then you can go back to chase the ghosts, and then you get a combo. And then you get more and more scores. So for human players invented two new terms or two new vocabulary, that's two words that monkeys doesn't have. One is save, and one is stay. So in Pac-Man, you can do something like left, right, left, right, left, right, and stay in the same place. So human invented these two vocabulary, save these energizer, and stay in the very near to the energizer. And then when the ghosts come close, the human player will hit the energizer and kill all the ghosts together to get a very big boost of the scores. But monkey doesn't have. So I think the main difference between higher level of intelligence and lower level of intelligence lies in two parts. One is whether they have the ability of formal reasoning. The other one, if they have the formal reasoning ability, then how open or how complicated their vocabulary is. So for a dog and cat, I think they have some kind of vocabulary. They have.
Yeah, well, I think you are very carefully evading the gist of my question, because the gist of my question wasn't about the formal reasoning in animals or like whatever, which I totally get, but the gist of my question was the very definition of a symbol.
Yes.
Right? So if the definition is crisp, you have a theory. At the same time, if the definition is not crisp and somehow rough, you
yes,
know.
I understand.
Yeah.
I'm going to, so I said these are two questions. So first one, I believe animals have formal reasoning power. The second one is that the concept itself. So symbolism has been criticized. Even Wittgenstein had very big change in his mind. So before, when he was young, he think everything should be formalized, and even philosophy should be formalized. And at the end of his life, he thinks that there are so many things that cannot be symbolized. And I agree, the second version actually. So what I am saying here is that if the task can be formalized, then we do formalization. But there are some concepts that you cannot really formalize. For example, I think in Chinese, I gave some example to my students. It's called, I know there are some Chinese students, so they must understand 好了好了，这下好了。Which means good, good. Now it's good. And the other is 坏了坏了，这下坏了。Bad, bad. Now it's bad. How can you formalize? And 好了好了，这下坏了。坏了坏了，这下好了。So good, good. Now it's bad. Bad, bad. Now it's good. So these are very good examples of that language is just a game. So inside of this game, for example, in a constrained environment, if the task needs some guarantee to be solved correctly or be verifiable, in this kind of problems, we need to formalize them. But for the examples like which I said before, it should be vague and should not be crisp. In that case, I think the large language model can handle that.